Right, so we are in section 15.2, part 2. All right, so before we talk about line integrals with vector fields, I want to talk about a couple of different kinds of application problems. So let's say the problem asks you you had a wire in the shape of a curve C with density rho equals f of xy. Find the mass. What is this problem asking us to do? This is the line integral. The mass equals the line integral over our curve of f of xy ds. Well, this problem is asking us to do a line integral. We have a curve, shape C, our density function is our f of xy, so this is a line integral question. So when you see that in your homework, see this kind of problem, it's asking you to do a line integral. How about a problem that says find the area of the lateral surface below z equals f of xy, above curve C in the xy plane. So what is this problem asking us to do? What's that?
Build a wall.
Build a wall. It's asking us to build a wall. So let me draw a picture. So here's my surface above the xy plane. Here's curve C in the plane, and we want the area of the lateral surface along this curve. So here's that curve projected onto the surface. So we're looking for the area of this little piece. So we're projecting the curve onto the surface, and we want the area of this piece here. So what is this asking us to do? This is also a line integral question. The area, we said we could think of the area as this line integral over C of f of xy ds. F of xy is the height. ds is the little base section. So we're adding up the base times the height as we move along that curve. So this question is also asking us to evaluate this line integral. So when you see a question that asks you to find the area of the lateral surface, it's asking you to evaluate this line integral also. So these are two different ways of asking, two interpretations, physical interpretations of line integrals that you'll be asked questions in these ways that really what they're asking you to do is evaluate the line integral. And the only stipulation with this example is that f of xy has to be positive. So we don't want our surface to go, f of xy to go above and below the xy plane. So both these kinds of questions are asking you to find a line integral. All right, now let's talk about evaluating line integrals on vector fields. In first semester, we did a little bit of calculation. We found the work done by a variable force, and we said that work equals the force, and we take the dot product with the displacement vector. And we said that the force only does work in the direction of motion. What we want to do now is find the work done by a force. So this is a particle moving along in a straight path. So we're going to think of what we're doing next as finding the work done by a force. We want to figure out a way, and our force can vary with x, y, and z. So we have this multivariable function that describes our force, a vector field. A force is a vector field. Moving a particle along a smooth curve C. So now our particle is moving on some kind of curve, and we have a force, a vector field that describes a force, and this force is going to do some work on that particle as it moves along that curve. And the curve isn't necessarily straight. So what we're going to do is draw a picture to describe this. This will get us to our idea of a line integral on a vector field. So here's our space. And hopefully the method that we use is familiar by now. Here is our curve C. So we have some curve here. And we're moving our particle from point 0, piece of 0, to some other point, piece of n. We're going to divide this curve up into small little pieces. So we're going to divide it into little intervals. And we're going to look at the work done right here in the ith interval. This interval has arc length delta s sub I. So it's the distance that the particle moves in that little section. And we're going to say this is a very small section, so we have the force done, the force at that particular point is this little vector, and we're going to say that is our force. Whoops. I want that arrow to be black. And that is our force vector at x sub I, y sub I, z sub I. So we're going to sum the work done by this force along each little portion that we divide the curve into. So let's magnify this little portion. I'm going to magnify this a little bit. So here's delta s sub I. So we're magnifying this little piece. Here is our force vector. And the force only does work in the direction of motion. Well, what is a vector that we've used that points in the direction of motion at this particular point? Not the normal vector, but the tangent vector. So the tangent vector points in the direction of motion. So here is our tangent vector. Here's our tangent vector at that particular point. And we're going to say this is our unit tangent vector. This is our unit tangent vector on that particular subinterval. So the force only does work in the direction of the unit tangent vector. So our small increment of work that's done by this force over this little interval delta f sub I is, I'm going to say delta w sub I, is our force at that particular point, x sub I, y sub I, z sub I, dot our unit tangent vector at that particular interval times delta s sub I. Delta s sub I is the distance that we're moving. We're saying this is very small, so we're assuming that we're moving essentially in a straight line. We sum this over the curve from where we start to where we finish. We take the limit as delta s sub I approaches 0. So this is our familiar argument by now. And we arrive at our definition of our line integral for a vector field. So we're going to sum these little bits of work, take the limit as delta s sub I approaches 0, and we end up with, finally, the work is the line integral over C of f dot t ds. And we're going to make this a little nicer so that we can evaluate this. Do we remember how we found our unit tangent vector at a particular point on the curve? We said our unit tangent vector was, what quantity gives us a tangent vector at a point on the curve? R prime. So our unit tangent vector was r prime over the magnitude of r prime. And ds was, and this we used this yesterday, was the magnitude of r prime dt. So I can simplify this integral and say that our work is the line integral over our curve of f dot r prime dt. And you'll also see this written as the integral, line integral C of f dot dr, where dr, we're saying dr is r prime dt. So this expression would give us the work done by this force in moving the particle from P0 to Pn along this curve. So we good with how we came up with that idea. So we're going to use this idea of the work done by a vector, by a force moving a particle along a curve to define a line integral of a vector field over a vector field for any vector. So we're not necessarily talking about a force. We're not necessarily talking about work. We can use the method to define our line integral of any vector field moving over some path C. So this is going to be our definition of the line integral over a vector field. So we make this our definition. The line integral over our curve C of f dot dr is whatever our vector field is dot a unit tangent vector ds, and the way that we evaluate this, the way that we're going to evaluate this is the line integral over our curve of f. We're going to parameterize our curve. So f of x of t, y of t, z of t. So we parameterized our curve. We express our force, our vector, in terms of the parameterization. And then we're going to take the dot product of that with r prime, which is a function of t, dt. And I want to put my limits in, from a to b. And we're saying that f is a continuous vector field, so our vector field is behaving nicely, our curve is smooth, and our interval along our curve is from a less than or equal to t, less than or equal to t. And c is given by r of t. So we parameterize our curve, and t varies from a to b. So this gives us a method to evaluate a line integral on a vector field. Very similar to what we did with the line integral for a scalar field. We express our vector field in terms of our parameterized curve, in terms of the parameters. We take the dot product with r prime of t dt. So we contrast that with our scalar field, where we expressed our scalar function in terms of our parameters, and we multiply that by the magnitude of r prime times dt. So now we have a way to evaluate a line integral on a vector field. What we'll do on Thursday is talk about a little different form of a line integral on a vector field, what we'll call a differential form. So just another way to work with this. And then what we're going to eventually do is talk about what happens when our vector field is conservative. When we have a conservative vector field, some very nice things happen with line integrals that can make our lives much easier when we're evaluating line integrals. All right, everybody good so far? So all I want to do next is just take a look at a few examples of setting these up and evaluating. Okay. So we want to evaluate the line integral c of f dot dr. Where f is our vector field, is xy I hat plus y j hat, and c, our curve, is given by this vector valued function for cosine t I plus 4 sine t j for 0 less than or equal to t less than or equal to pi over 2. So first off, what is our curve? Oh, I forgot one thing. The way I wrote it is an ellipse, but I want to do this. So what does that make it? Circle, 0 less than or equal to t less than or equal to pi over t gives us, what's that? A quarter circle. So we're talking about a quarter circle here. Our path is a quarter circle. To evaluate this line integral, we're going to write f in terms of our parameters. So f is going to be 16 sine t cosine t I hat plus 4 sine t j hat. We need r prime to evaluate our line integral. So we take r prime. R prime is going to be minus 4 sine t I hat plus 4 cosine t j hat. And then our integrand is going to be f dot r prime. So f dot r prime, we get minus 64 sine squared t cosine t plus 16 sine t cosine t. So our line integral, integral c of f dot dr, is going to be the integral from 0 to 2 pi, or sorry, 0 to pi over 2 of this quantity. So minus 64 sine squared t cosine t plus 16 sine t, going to run out of room here, cosine t dt. And our integrand sets us up nicely for, we have nice easy integrals. So this is minus 64 thirds sine third t plus 8, 16 divided by 2, and I'm going to use the sine, so sine squared t, and we're going to evaluate that on 0 to pi over 2. And when we evaluate that, we get minus 40 thirds. So that would be the value of that line integral. And if this were a force that were acting on the particle moving along this quarter circle, the force would do negative 40 thirds units of work moving the particle along that quarter circle. Similar. Just trying to decide which one, which other example I want to do. Before we do another example, we said yesterday that the value of our line integral for our scalar field was independent of the parameterization. So the mass of our wire, the area of that surface doesn't change if we go one direction on the curve or another direction on the curve. What happens, what's going to happen with our line integral over a vector field if we change the orientation of the curve? It would change the sign. If we're thinking of it as work, so we're talking about the work done moving one direction versus work done moving the other direction. So changing the parameterization can change the sign of the value of this line integral. So the parameterization, the absolute value of our line integral is independent of the parameterization, but we can end up with a change in sign. So one thing to be aware of, the difference between scalar vector fields and or scalar line integrals and vector line integrals. All right, let's look at one last example. Just another example calculating a line integral on a vector field. So for this one, we want the work done by F equals yz I hat plus xz j hat plus xy k hat. Moving a particle from 0, 0, 0 to 5, 3, 2. All right, so we have our force. We're moving our particle from 0, 0, 0 to 5, 3, 2. What do we need to do to solve this problem? We need to find a vector. We need to find PQ. Do we need a vector for our line integral over a vector field? We need some kind of vector. But is it going to be just a single vector?
What do we need to use this
We need to parameterize the line from 0, 0, 0 to pi 3, 2. We need parametric equations for the line because we need r and r prime. We need to do f dot r prime. So we need parametric equations for our line to do f dot r prime. Or we could think of the unit tangent vector. What would be r prime? Thinking along the lines that Will's thinking, what would be r prime for the particle moving from 0, 0, 0 to pi 3, 2? What vector would point in the direction of r prime? Wouldn't it just be the vector from 0, 0 to 0 to pi 3, 2? That would be the vector that moves in the direction of r prime. So we could write parametric equations for our line, but our r prime is going to be, when we take the derivative, the numbers that are our direction numbers. The direction numbers from our vector are the coefficients in front of our t when we parameterize our line, when we write the parametric equations of our line. So r prime, for this particular example, is just going to be the vector 5i plus 3j plus 2k hat. So we could write parametric equations for our line. Then we would have to take the derivative of, take the derivative of that vector. The derivative is just going to give us the direction numbers. But what we do need to do is express f in terms of our parametric equations. So we do end up needing to write the parametric equations of this line. So, do we remember how to write a set of parametric equations for our line? X equals x0 plus at, y equals y0 plus bt, and z equals z0 plus ct, where ABC is the direction vector. So those are our parametric equations of our line. So our parametric equations for this line, for the line is r of t equals, and we're going to use, it's nice because we can use 0, 0, 0 for our x0, y0, z0. Our direction vector is just the vector from 0, 0, 0 to pi 3, 2. So our direction numbers are 5, 3, and 2. So our r of t is 5ti plus 3tj plus 2tk hat. And then we need to express f in terms of our parametric equations. So f here is going to be yz I hat. So we get 2t times 3t, so we get 6t squared I hat plus xz, so we get 10t squared j hat plus xy 15t squared k hat. And then we're going to integrate f dot r prime. And we decided r prime was this vector. We can also see that from here. So f dot r prime is going to be 30t squared plus 30t squared plus 30t squared. We get a 30t squared from each component. So I get 90t squared. So my integral, so the work is going to be the integral from, and I need my limits on my limits of integration. As we move from 0, 0, 0 to 5, 3, 2, t varies from what to what along R? 0 to 1. So the work is going to be 0 to 1 of 90t squared dt. So I get 30 t cubed evaluated on 0 to 1, which is 30. So that force would do 30 units of work moving the particle along that line. So when we evaluate a line integral on a vector field, we always have to express our vector in terms of the parameterization of the curve. So we ended up having to parameterize that line, even though we could figure out our prime figures. All right, questions there? Why does it go from 0 to 1? So if our position vector is given by 5t I, 3tj, 2tk, to go from 0, 0, 0, t has to be 0 to get the point 0, 0, 0, and to go from to 5, 3, 2, for our position vector to be 5, 3, 2, t would have to be 1. So that's going to take us from 0, 0, 0 to 5, 3, 2. All right. Homework. There we go.